This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Gregory Kaphammer. I'm excited to introduce Samuel Colvin. He's our guest today as we talk about systems like Pydantic, Pydantic AI, and Pydantic Logfire. Samuel is the CEO and founder of the Pydantic company, and he's really well known in the Python community for building a wide variety of cool tools, three of which we're going to dive into today. Samuel, welcome to Software Engineering Radio.
Thanks so much for having me. Yeah, really looking forward to our conversation.
I'm really looking forward to the conversation as well. So we're going to talk about three tools, and they have similar names. And before we dive into the first tool, I'd like to get like a high-level understanding of what those three tools are and maybe how they're connected to each other and how they might leverage each other. So the first question for you is, what is Pydantic? Can you help us out?
I can. It's not always the easiest question to answer directly. So Pydantic, to all intents and purposes, is a data validation library for Python, but it does a bunch more stuff above and beyond simple data validation, like controlling serialization, coercion when you're validating, and generating JSON schema.
Okay, that's helpful. We'll dive into more details in just a moment. But the next quick question, what is Pydantic AI and how is it connected to Pydantic?
So Pydantic AI is an agent framework or a library to interact with LLMs from Python. It uses Pydantic, and obviously it's built by us, the same team. Pydantic is very widely used in interactions with LLMs, in particular validating structured outputs. So hence we thought it was a relevant thing for us to go and build.
Yeah, that makes a lot of sense. And I've used other LLM frameworks, and I even noticed that they're using Pydantic. So I can imagine why it's helpful to have the AI framework that comes from the Pydantic team.
Yeah, exactly.
Okay, and then quickly, the third question, what is Logfire and how does Logfire connect to the other systems that we mentioned?
So Logfire is an observability platform. So we do logs, traces, and metrics, let you understand, monitor your application. It is very useful when you're building applications in Python in general, but particularly AI applications. So it works nicely with Pydantic AI, although we're very keen on building on open standards. So you can use Logfire with anything that speaks OpenTelemetry, and you can actually use Pydantic AI with anything that will receive OpenTelemetry.
You mentioned a moment ago open standards, and we're going to start talking about Pydantic and some of its key features and how you built it and refactored it. But for our listeners who haven't tried it yet, it's important to note that Pydantic is an open source tool, and they can go to GitHub and they can try it out. They can pip install it or UV install it. And so it's really a great framework for them to get up and running if they've never done data validation in Python.
Yeah, absolutely. So we're very keen on open source and on contributing to the open source system. So Pydantic is open source, MIT licensed. All of the building blocks are obviously also MIT licensed. Then Pydantic AI is also open source and MIT licensed. So you can go and use it. You can even copy bits of it, as certain companies have done recently. Although Logfire, the back end, is closed source, because that's our commercial wing, and we think it's important to be clear where we're being commercial versus where we're contributing to open source. But again, we're building on open standards that we'll come to later. But even within Logfire, our SDKs for Python now, but for other languages coming very soon, are open source and MIT licensed again. So you can use them and send the data to the Logfire backend, we hope, and pay us eventually, but also to anything else that speaks OpenTelemetry.
Sure, that makes sense, and that's a helpful response. Let's talk quickly about data validation. You mentioned it a moment ago. Can you say in more detail what is data validation, and then maybe give a concrete example of how a programmer would do data validation with Pydantic?
Yeah, absolutely. I think the main thing that I neglected to include when I first described Pydantic is that we use type hints in Python. So type annotations like string or int or list of integers, etc., to define the schema that we use for the validation. So the best way to think about it from a high level is if you are new to coding, your first week of writing code, you get told that you're going to write this computer code and it's going to be interpreted by a machine. And so you need to be very precise in how you define everything. And you make what seem like trivial mistakes and then the program crashes. And yet, as you start to learn Python, you will be shown data classes, for example, where you define your fields and you add a type annotation which says this thing is going to be an integer, this thing is going to be a string, this thing is going to be a dictionary of strings mapping to lists of sets of integers or whatever it might be. And then you go and initialize your data class, and actually you can use whatever type you like. And sure, your IDE might complain and put a little squiggly line underneath, and if you get to using a type checker, that will complain. But actually at runtime, you can pass whatever types you like. And of course, in some cases, that's easy, that's useful as a kind of way to escape the constraints of the language, but often that's not helpful. You want to, for yourself, be warned or error when you pass the wrong types, but that becomes even more important when you start to load data that someone else has generated or receive data someone else has written. So whether that be parsing a CSV file, processing an API request, loading data from an HTTP form, accepting input from the terminal, anything where you have basically the boundaries of your application where you're receiving data that doesn't fit within the typing system, type hints are basically useless because they're not enforced at runtime. And so what Pydantic basically does is take those type hints and enforce them.
Okay.
But we do a bit more on top of pure enforcement. So we will, in general, although we have a strict mode where this doesn't happen, we will coerce types where you would want to. So for example, if you have a integer field and you pass it the string 123, Pydantic will identify that that string would be valid as an integer and coerce it to an integer. And so you will get 123 into that field instead of an error.
Okay. So first of all, it's important to point out, like you said a moment ago, that by default, type hints or type annotations, they don't actually play into the running of your Python program. But if you use a tool like Pydantic, it can run in either a strict mode or a data coercion mode, and it can help you to validate or confirm that you're getting the data that I expected. Is that the right way to think about the tool so far?
Yeah, absolutely.
Okay.
But often what you find once you've done this validation and you have your data in Python is you will also want to go and serialize it to another format. So export it, either marshal it to a simple dictionary, for example, or output it to JSON. And so as well as doing the validation and indeed parsing JSON, we will also serialize data to JSON or to Python objects with a bunch of control over exactly how that happens. And then the third bit is generating a schema for your types. So let's say you define a Pydantic model or a data class which says we have, let's say it's a user sign-up form. So we have the user's name, we have their email address, which we need to be a valid email address. We have their date of birth, which is going to be a date field. Then as well, we can obviously do the validation. I've said we can do the serialization, but we can also generate JSON schema, which is an open standard that defines the fields of that form, for example. And so that's useful in lots of contexts in LLMs, but also in general web development where you can use that schema to define your form on the front end.
Mm-hmm. A moment ago, you mentioned strict mode versus data coercion. Can you give a more complicated or real-world example of data coercion, like in the context of AI or a web application?
Yeah. Internally, we refer to strict mode versus lax mode. And the principle of Pydantic, prior to V2, we only had what we would now call lax mode, so it was always coercing. Now we have that switch across the whole of the library. But there are lots of scenarios where often you just can't generate the right data. So, for example, if you're receiving JSON data, you can't have a date. So you have to be able to take, for example, a string and coerce it to a date object in Python. If you're parsing URL arguments or environment variables, everything has to be a string. So you can't even submit an integer. You have to submit a string, which will then need to be coerced to an integer. So there are lots of scenarios where we need that coercion for things to make sense. But there are also many scenarios where a user gets something wrong or an LLM gets something wrong when it's generating data. So perhaps you submit a list when the application wants a tuple, or you send in a set when the application wants a frozen set. Or as I say, you submit a string in ISO 8601 format representing a date rather than the date object. And so we have fairly fine-grained control over where and when we will coerce things to the correct type. As you can imagine, that comes with a bunch of nuance. It's not exactly clear when you should coerce and when you shouldn't, but we try to follow a bunch of sensible rules and be explicit about when we will and won't coerce. But the high-level principle, which we can stick to, is whatever you define in your Python types as this is what I want, we will guarantee you, or as far as any open source library will ever guarantee, we will guarantee you that that's the object you will get.
Okay. Now, a moment ago, you also mentioned data serialization to JSON. Can you briefly say what's serialization, and then how do you serialize it in Pydantic to a JSON file?
Yeah, absolutely. So serialization is the process of going from types in the language, so a Python dictionary, a Python date, a Python string, etc., to some external format. Pydantic has specific support for serializing to JSON. So we will take the Python object that we validated in general, and we will serialize that to JSON. And we have some control over where you can customize that, where you can, for example, omit none values or omit default values or omit specific values in general. Also how you might change the serialization format for, say, a date, etc., etc. The other bit I missed to say is that within Pydantic v2, we also have specific support for parsing JSON. And that's actually very important because you can imagine in some scenarios, in strict mode, if you only ever validated the Python object you got out of parsing JSON, you could never construct a date because strictly you can't define a date in JSON. And so if Pydantic was only able to operate on the Python object you got from deserializing, you could never have a date field. And so what we're able to do is have strict mode, but because we know we're parsing JSON, we now say that strictly in JSON, a date must be a ISO 8601 date format, for example. And there are many other examples. For example, you might have a path. You can't have a path type in JSON, and so you would need to accept a string as the input to that. So there's a bunch of nuance in there, but yeah, as well as doing the parsing of JSON, we'll also serialize to JSON.
Okay, so that's helpful. And you've mentioned V2 several times, and we're going to dive into V2 and how it was rewritten in Rust, and we'll talk about all the performance improvements that came with that. But before we do that deep dive, can you give us like a success story or a concrete example of a system that actually uses Pydantic for some kind of large-scale data validation or serialization?
Oh, there's so many examples, some of which I have some understanding of. So, for example, many banks, I can think of 5 or 6 now, but maybe they don't want me to name them, will use Pydantic for validating the data they receive from interbank transfers. So obviously a very critical task where you absolutely want to be sure that you're getting the right types of data. They will use it for that. NASA use Pydantic quite widely. For example, the services they built to show the imagery from the James Webb Space Telescope is built on FastAPI, which in turn is built on Pydantic. As I say, we'll talk more probably about the LLM specific case, but parsing the output of structured data. So all of the model SDKs, but also the agent frameworks are using Pydantic for that. Yeah, such a wide range of applications, many of them proprietary and internal. But I know, for example, inside Microsoft, inside Google, in Google Drive, there's an awful lot of Pydantic under the hood. I know inside OpenAI, there's enormous amounts of Pydantic going on, both in their training and in their inference side. It's all over the place because Python's great because it is not strictly typed, but there are so many boundaries of your application where having that strictness is useful.
Okay. That was a great response. So it's clear that we're using this kind of system for data validation and serialization across a wide variety of domains, open source projects, and different companies. And I know when I read the documentation for Pydantic, which is something I've been using for years, you often say V1, and then sometimes, and we've heard you say it now, you say V2. So what's V1 and what's V2 in the context of Pydantic?
Yeah, so Pydantic started off in 2017, obviously pre-version 1 as a completely side project. In, I guess, around 2019, we went to V1 and we obviously became more stable in the library. But at the beginning of 2022, Pydantic's adoption had grown enormously. It was still a side project for me, so I would try to spend an hour or so helping people in the evening after work. But it was still, as I say, a side project for me. But the internals of Pydantic v1, it was all Python. I wasn't particularly proud of the internals. And so beginning of 2022, I started working full-time on Pydantic, rebuilding the core in Rust. So there's an amazing library called Pyo3 that allows you to write Python extensions in Rust, which gives you an enormous performance improvement. But it goes beyond simply the performance. It allows you to write fundamentally more robust and scalable and maintainable code when you're building these big performance critical complex applications. And so I started off on what I thought was going to be a relatively quick project or a 3 or 4 month project to rewrite the core of Pydantic in Rust. That ended up taking about a year and a half. And I started a company, Pydantic, in the middle of that process, hired a team. And it was only because I was able to hire a team that we were really able to complete it. But today, Pydantic v2 is way ahead of Pydantic v1 in terms of usage. And we got somewhere between 5 and 80 times performance improvement for validation and serialization out of doing that upgrade. And I think it has been part of the thing that has cemented Pydantic as kind of the default way of doing data validation in the Python ecosystem.
So Python v1 is a pure Python implementation, and then v2 is rewritten in Rust. There was an episode of Software Engineering Radio about whether you decide to refactor or to rewrite. You must have gone through some interesting discussions to decide to rewrite Pydantic in V2 using Rust. So, what were the technical challenges that drove this rewrite, and how did you decide to rewrite versus refactor?
You said Python V1. Pydantic V1, yeah, it was pure Python, and V2 uses Rust. Look, I'd love to say that we had some grand vision. I was super compelled by Rust as a way. I spent a few days prototyping. I became convinced this was going to give us a massive speed up, and I kind of got building. At the time, there was some very nice people, Eric in France and Hassan, who still works with me in Germany, helping me do some maintenance, but the vast majority of it was me on my own. And in terms of that decision to do the rewrite, that was just me sort of experimenting and going off and trying. And like so many technical projects, it would probably never have happened if I had known how hard it was going to be. It's the naivety and the curiosity are the thing that drive projects that end up, I think, making things much better. But no sort of simple sit down and try to analyze the strengths and weaknesses or the pros and cons for this project would have resulted in it happening. It was a result of, like I say, this naive curiosity.
A moment ago, you mentioned Pyo3. Can you tell us a little bit more about what that is and how it helps Python communicate with Rust?
Yes. So obviously CPython, which is the version of Python most of us use, is written in C. And it has what they call an ABI, which is effectively an interface to the dynamic library that allows you to extend Python using C. So the point is that there are hook points into, you effectively write a DLL, a binary library in your chosen operating system, and Python knows how to look inside that and pull out functions that it can call. And that has been used for years. So libraries like NumPy use that extensively to write the most performance critical parts of the code base. The problem is that most of us don't want to be writing C. It's extremely easy to make mistakes. It's extremely hard to be productive. And the errors that can result, like memory errors, are particularly catastrophic because your application will just crash on the spot with segfaults. Or even worse, it will just go and behave in some unexpected way, but continue to apparently behave. And that's where we've had many of the worst software bugs have happened over the years have been a result of those memory errors. So Rust is a language that originally came out of Mozilla, which tries to be as performant as C, but avoid those risk of memory errors in particular. And it has an amazing developer experience, amazing ecosystem of libraries. It feels in many ways like working with JavaScript or Python, but with the low-level control and performance you would get from C. And so Pyo3 is a project that allows you to effectively, ultimately build those same dynamic libraries but writing Rust code instead of writing C code. And so David Hewitt, who I'm very pleased to say I work with, who works with me on Pydantic, is the main maintainer of Pyo3. There's a bunch of other people who contribute a lot, but yeah, it tries to be a way to let you write Python libraries, but in Rust.
Okay, so you can go basically from your Python program's address space to the Rust version of Pydantic. So there's some overhead you would think in terms of Python calling Rust. And it turns out to be the case, however, counterintuitively, that Pydantic version 2 is significantly faster than version 1. So can you maybe dive into more details? Can you tell us why it is so much faster than version 1?
So there is very little overhead. So as I say, when you're writing Python code, in the end, you're writing instructions to a C program as to how to execute, right? Because in the end, Python itself is written in C, or the main version most of us uses. And so Rust effectively gives us low-level primitives to write C functions, effectively, functions that C code can call. And so there is a tiny, it's in the order of single-digit nanosecond overhead to calling a Pyo3 function. Some of that will go away eventually, but Rust is somewhere, depending on what you're doing, 100 times faster than Python code to execute. And so although you have this minuscule overhead for calling the Rust function, that is much more than made up for by doing all of the rest of the validation in Rust. And the point is you get to operate with a mixture of pointers to Python objects. So let's say you have a Python dict that you can interact with in Rust, you can iterate over it, you can add members to it, etc. But you can also, let's say you have a string, you can have a PyString, which is a pointer to the Python string object, but you can also get out of that a Rust string object, and that allows you to then go and operate on the low level of Rust and operate on that string. You can pass that string around by reference very cheaply in a way that Python, when you pass a string to a function, you're not passing by reference in the same way.
Okay, that really makes sense, and I'm glad you gave those additional details. Now, I looked on the website and I remember you a moment ago saying a similar number, but Pydantic V2 is either like 5 times up to 50 times faster, and it's commonly about 17 times faster. And I know you have a benchmarking framework, and you must have needed to repeatedly run benchmarks in order to gauge how good of a job you were doing at the rewrite. So can you tell us a little bit more about your benchmarking process?
When I was working on Pydantic Core, which is the Rust component, so Pydantic V2 is split effectively into 2 libraries. We have Pydantic Core, which is basically the Rust code, and then we have Pydantic itself, which has Pydantic Core as a dependency. Pydantic is responsible for basically taking those type annotations and turning them into what we call core schema, and then you can take a core schema, which is a relatively simple structure of dictionaries, etc., which defines the schema, and then Pydantic Core will take the core schema and turn that into a schema validator and a schema serializer, which are then Python objects which are using Rust code, which you can then use to perform the validation. And so when I was working on Pydantic Core, I spent a lot of time doing benchmarks to try and work out where to eke out a bit more performance, where the slowdowns were coming from. I started off using the PyTest benchmark library that had a number of drawbacks, and so I ended up implementing PyTest Speed, which is for the most part API compatible with PyTest benchmark, but has a few quality of life improvements, nicer tables it will spit out in terms of showing you those benchmarks. PyTest Speed is not heavily maintained by us anymore, but it was very useful at the time, and I think it still works well. But then partway through that, Arthur got in touch with me, who was looking into starting a company. What he's built is CodSpeed, which is basically a continuous benchmarking framework. So CodSpeed does 2 things. One, they have a way of running your benchmarks using Valgrind. Valgrind is a way of measuring the number of CPU cycles that are performed when you execute some code rather than measuring the time, which means you can run benchmarks in a noisy environment like GitHub Actions and get reliable outputs. And then the second thing they have is basically a view where you can see how benchmarks change over time, and it will literally ping up on a pull request and say, this pull request is failing because this benchmark has got worse, or lots of green ticks if the benchmarks have got faster. And that allows us to continue to improve performance, but also detect when there are regressions and go and improvement. And even better nowadays, if you look at CodSpeed, they will give you a flame diagram, a flame chart of which bits of the execution are taking what amount of time, and then where the change is coming from. So you can get like a very nuanced description of how the performance is changing in a given benchmark. So it's awesome. Although that CodSpeed came about as we were working on Pydantic, we use it heavily on Pydantic Core and on some other libraries.
That's interesting. I actually didn't know that there was an integration with Valgrind, but I can imagine that being incredibly helpful.
Yeah, it works really well because it means we can run the benchmarks on CI. They get sent to CodSpeed. CodSpeed then puts the comment onto the pull request saying, here are the improvements, here are the deteriorations, and we can be pretty confident that we don't randomly introduce big slowdowns. But that's only half the work. I think we have probably ballpark 100 different benchmarks to measure the different performance aspects of Pydantic Core, because there are so many different things that you're doing. You think it's like simply doing validation, but it can be as simple as we have whatever it is, 40 different types that we validate and combinations of them and serialization. And we have JSON versus Python, et cetera, et cetera.
So I have one more question about the rewrite, and then I want to talk a little bit further about how people might extend Pydantic or connect it to other tools. But just quickly, as you were working on the rewrite, at what point did you feel confident that, hey, this is going to pay off, and I'm definitely going to get a system that's better than V1?
From very early on, I was able to get benchmarks that showed validating simple things that was showing the kind of, 10, 20x speed up, which is massive, right? Because we talk generally about 5%, 10%, 20% speed ups. This is 10, 20x improvement in performance, which is massive, right? I mean, I was confident from the beginning it was possible. I suspect probably too much so at times. I think that, I'll be honest, anyone who's worked with Pydantic V2 will know that the challenge of migrating from V1 to V2 was quite big. We probably didn't do a good enough job of reducing the complexity of upgrading. In particular, we, as well as the rewrite in Rust, we also fixed a bunch of APIs that we thought were wrong from V1, but that meant that the overhead of upgrading was relatively large.
Okay, so there were changes to the API that means people have to actually write Pydantic code a little bit differently in V2 than they do in V1.
Yeah, exactly. Well, we tried to a certain extent to have fallback functions for the old names and deprecation and stuff like that. But there were also these subtle changes where we had basically fixed the semantics of where we would coerce and where we wouldn't, which are much harder to detect from a simple, review the code. And yeah, I know a lot of people have had trouble with the upgrade from V1 to V2. It's made particularly difficult in the Python ecosystem because you can't install two versions of a package. In Rust or in TypeScript, you can install two different versions of a package. So if two different libraries you're using use different versions of some third library, you can install both of those versions. In the Python ecosystem, that's not the case. So for example, FastAPI upgraded pretty quickly to V2, but LangChain took much longer to upgrade to V2. And so there was a long time when you couldn't use the latest version of FastAPI and LangChain. And that caused a lot of friction, both for the library maintainers, but also for library users.
Yeah, the pain you're describing of a Python programmer is one that I myself have experienced many times. Especially, it's more painful if you have also programmed in Rust or JavaScript. You mentioned FastAPI, and I should share with our listeners, we also had an episode about FastAPI, and I'll make sure to link to that in our show notes. What I wanted to do very quickly is talk about ways in which you can connect Pydantic to other types of systems. For example, I know you can connect Pydantic to Redis or to a relational database through like SQL Alchemy. So can you tell our listeners a little bit more about how they can connect Pydantic to other types of systems?
Yeah, there are lots of different libraries for doing this. ORMs in the case of relational databases, what are called ODMs in the case of databases like MongoDB and I guess Redis. But the principle comes back to the same thing I was talking about earlier. One, you have to do this kind of upcasting of types. So you might not get back a data object from, say, Redis. You would get back a string, and you need to do that coercion, but you also want to make sure that what your application is expecting in terms of a field type matches what's actually there in the type. And so lots and lots of these libraries for connecting to databases use Pydantic under the hood to perform validation and serialization in a highly performant way. Yeah, so you can go and look. I think the main Redis library has integration with Pydantic. The SQL model from Sebastian, the same person who built FastAPI, which built on top of SQL Alchemy and Pydantic. There's Beanie for MongoDB and a myriad of others, not all of which I can exactly name right now. But yeah, lots and lots of different tools that use Pydantic and allow you to connect to data stores of different types.
So the way that I think about it is that if your ORM uses Pydantic, you can have more confidence in the correctness and the reliability of your interaction with the ORM because of the fact that it's using Pydantic. Am I thinking about it the right way?
Yeah, absolutely. And also, as the maintainer of those libraries, there's a bunch of less work to do because you don't have to worry about every single time, how am I going to do the translation from a Postgres wire protocol date format into a Python data object. You can rely on Pydantic to do it correctly. And if Pydantic's doing it wrong, we go and fix it once in Pydantic, and then everyone benefits from it.
Sure, that makes a lot of sense. So let's talk a little bit now about Pydantic AI, which is another system that you and your team are building. My impression is that Pydantic AI helps me as a programmer interact with LLMs. Can you pitch for us at a high level, what does Pydantic AI do, and how does it leverage all of the things we've talked about already?
Yeah, absolutely. So there are kind of two sets of problems in interacting with LLMs. One is that we all want to build in a model agnostic way. We want to be able to switch in and out the different model providers very quickly, or inference providers. So none of us know yet which model is going to be most performant. Over the last year or two, as these models have scaled up, as these companies have scaled very quickly, they haven't always been the most reliable in terms of uptime. So it's very useful to be able to switch between models for that reason. But it's mostly about not knowing which is best for our application today, let alone which is going to be best for our application tomorrow and in a year's time. So the number one piece of value I think that Pydantic AI brings is this model agnosticism. You can switch in and out OpenAI, Anthropic, Gemini, Grok, DeepSeek, etc., Mistral, Cohere with one line of code. But above and beyond that, although all we're doing fundamentally is making these API requests and processing the responses, the systems of interactions that people are building, in particular agentic workflows, have got relatively complex, and we don't want to have to manage every single, I'm going to make this API request here, I'm going to process the response here. Although there is an awful lot of unknown and an awful lot still to be decided in terms of best practice of using LLMs, there's a bunch of stuff we are confident of. So, for example, everyone from LangChain to CrewAI to PyData to small agents, etc., all of the agent frameworks, Llama Index as well, are using Pydantic to define the schema for structured outputs, whether that be tool calls or other forms of structured outputs. The point being, you define a Pydantic model or a data class or whatever else. Pydantic will then go and build a JSON schema. You then pass the JSON schema to the model. as the definition of, for example, the parameters for your tool call. The model then returns you some data that may or may not match that schema. If it passes, we always want to do the coercion, so the upgrades to full Python types because we're getting back JSON. If that passes, great, we can then go and call our tool or process our structured output. But if it fails, we then want to encode a description of the errors, pass that back to the model and ask it to try again. And I think it's fair to say now that given Pydantic's been around for a long time and has been being used for this use case for a while now, models are actually trained directly on Pydantic errors. And so they do particularly well at basically taking a Pydantic error and interpreting how to correct the data they're returning to match the schema that they're asked to generate. And so we generally call that thing reflection. And that's another thing that Pydantic AI has out of the box that people generally want to use. But the other bit is this loop. The general agreement on what an agent is effectively a for loop where you're asking a model to perform an action, looking at the structured output, deciding what to do next, and going around in a loop. And that, again, there's no reason why you should go and implement that loop yourself. Why not use Pydantic AI that will go and implement that for you? But still, the principle is to give you the low-level control if you want to, that allows you to decide exactly how you want your model interactions to behave if the defaults we give don't work well enough, or if you're doing something esoteric enough that the default doesn't work.
Okay, so I can use Pydantic AI to give structured content to the LLM, and when the LLM returns, then I can kind of use Pydantic again in order to validate its response. And then you talked about the agent as being like a for loop, so it sounds like Pydantic AI also has features for steering the interactions with the LLM. Am I summarizing it correctly?
Yeah, you're summarizing agent type well, and that is our primary kind of interface for interacting with models. We also have within the Pydantic AI repo Pydantic Graph, which is a finite state machine library, in theory, that has nothing to do with LLMs. You can use it to go and build things that are effectively equivalent to finite state machines, but type safe in the same way that Pydantic is type safe, unlike most finite state machine libraries in Python. That is particularly useful when you're building the more complex workflows where you have a complex system of state and you want to manage that in a robust way. But yeah, in the simple case of using our agent type, it's basically this idea of a for loop where we go and generally call a bunch of tools until we arrive at some answer and then end.
So you mentioned state machines, and that's something that I wanted to dive into in greater detail. Can you say briefly what is the state machine? And then how does my Python program use the state machine to help me build an AI-driven application?
Yeah, so I started off as a cynic about the state machines. I hadn't ever found them that useful in application development. And the main reason for that is that most state machines are fighting your application itself. So although we don't think of it this way, applications always have a state. And that state is whereabouts in the code you're currently executing. So to give a completely different example that I found really interesting when I identified what was wrong, we have this JSON parser that we use within Pydantic. It's very fast, but it also allows us to do iterative JSON parsing. So basically parsing, returning data as we parse the JSON. And when I started implementing the JSON parser, I was like, oh, well, we're going to need a state here. The state being like, I'm inside a string, I'm after a string, I'm inside a list. And you can imagine this might be some kind of stack of different states as we go into recursive objects. And it just wouldn't work, and it wouldn't work. And I tried to change the different states, and I tried to change how the application worked, and nothing was working until I realized. And obviously, I was very concerned about performance. So even if I got something to work, if it wasn't fast enough, that wasn't good enough. And what I realized eventually was I didn't need the state machine, because actually the application, how it was running, was the state. If I'm in the parsing string function, I know the state I'm in. And if I've called that from inside a list, I know that when I exit that function, I'm in the list. And so the complex hierarchical nested set of states that are parsing the JSON data are fundamentally defined by whereabouts in my application I am, not by some external state management object. So it's very important if you build a state machine, whether you use an existing state machine library or you implement it yourself, that you realize that you need your state machine not to fight with your application state, because that's always going to win. It doesn't matter if I tell my application, oh, I'm in state A. If I'm in the middle of calling function B, it's not going to work, right? Like the absolute winner in terms of state is always going to be where my application is. And so what we wanted to do was build a state machine library that gave us the biggest advantages of finite state machines and graphs, without fighting the application itself. And so we have this system where we use effectively the return type, just as we use type annotations in Pydantic to define how validation is going to be performed, we use the return type of our node runners to define what nodes can be called next. And so there are really 3 or 2 advantages of state machines. The first is that we have effectively guardrails on how to define our application, which make it very clear what is going on. And we can get nice things like we can get a mermaid diagram of the actual graph of our application's execution paths straight out of code. That is not an alternative definition. We don't have 2 sources of truth. We have our code with our type annotations, and from that we can generate a mermaid diagram. The second is that these complex systems don't run in one nice Python process where they run end to end. They are always going to be interrupted, whether they are interrupted because they need to be distributed across lots of compute, or whether they are interrupted because they take a few seconds to run and might be interrupted, or because they might require the full execution of the graph takes weeks. So if you imagine, for example, the returns process for an e-commerce company, you can do this now. Go into Claude and ask it to give you a complex state machine. It will print you out a lovely mermaid diagram of the returns process for an e-commerce company. And that's really neat. And if I go and build my simple throwaway demo, it's nice because I can be like, oh, and now the item gets returned, and I'll have like a loading icon for 2 seconds. And now within that same process, I can go to the like package arrives at the warehouse. In reality, of course, that's not how it works. That package takes a week to be returned, and I can't have the same Python process hanging, waiting for the item to be returned. And so we need this complex set of different entry points into our application code. And that is where state machines become so useful, because you can worry about writing your application logic and defining your graph, and Pydantic Graph will take care of allowing you to re-enter that graph in any point. And I think the most compelling bit of graphs is that whenever I've tried to build these things myself without a graph, the code required to manage re-entry in numerous different places starts to dominate. We end up with a spaghetti code, and the core logic, which is often very simple, gets completely obliterated by the complexity of re-entering the graph. And so it's this like interruption of execution and eliding that behind nice primitives that is so valuable within graphs.
So it seems like at a high level, we're talking about 2 main approaches for using Pydantic AI. The first approach is what you called the for loop agentic approach. And then the second approach is the graph-based approach that uses state machines. Can you help software engineers decide when would they pick one approach versus the other? And then how would they go about building and testing it depending on the approach they pick?
Yeah, absolutely. I mean, I think it's worth saying that they were both the same thing ultimately. Under the hood, now our agents actually use Pydantic Graph to define their execution. This is really valuable because it allows you not only to run an agent to completion, but you can also iterate over the subsequent steps, just as we allow you to iterate over a graph. And similarly, within a graph, if we want to have LLM interactions, we can call an agent from within a node. So effectively, we have graphs within graphs. You don't need to think of it that way. You can be like, now I'm just going to go and call an agent and ask it to return some structured data and then decide what node to call after that. But that's what's going on under the hood. In terms of when should you use a graph, I'll say now that there's a somewhat humorous and perhaps slightly overbearing warning at the top of our graphs documentation saying don't use them unless you're sure. I think that should probably be toned down a little bit. I wrote it when I first released graphs. I didn't want to do what certain other library maintainers do and basically say, oh, you should use our most complex and shiny thing for everything. I think there are lots of applications that don't need it, and you should basically be deliberate and considerate when you're working out whether or not you need a graph. My suspicion is, which is a really unhelpful answer, you'll know when your application is getting complex enough that you need that graph, and you'll probably have to go and rewrite it. But it's probably, unless you know exactly what you're doing, a mistake to start off going and using the graph. So the analogy is basically saying graphs are like a nail gun, and lots of things will be better solved by using a hammer. So my suggestion would be to kind of torture the builder analogy a bit further. Use a hammer until you're like, this isn't working, I obviously need something better, and then go and use the nail gun when you're ready, and you'll have a lot better time having learned how to do things with the hammer. And the problem comes when people start with a nail gun, get carried away, and that doesn't make them a better builder, it makes them a builder with a nail gun.
Okay, so ultimately, the underlying implementation is graphs and state machines, and maybe I should start as a developer with the simpler approach. Ultimately, it's going to emerge that my system is getting too complicated, and I'm trying to manage too much state on my own. And then at that point, perhaps I want to jump into fully learning how to use the graph-based approach that is built into Pydantic AI.
Yeah, that makes sense. But the other thing I'll say is, and this is the reason I think our nail gun warning is too overbearing, is these graphs are not that complicated. They're not doing anything particularly sophisticated in terms of your code. They're a bit more boilerplate. We have 3 generics on a graph because we're working very hard to remain type safe. So you'll have to deal with them. But it'll basically mean that you have 3 or 4 lines of code for every extra lines of code for every function you define, which is a bit annoying if it's not as elegant as just having functions, perhaps, but it's not enormously complex. And you will see that the actual execution of these graphs is actually pretty simple. It's basically call run on a graph node, get back another graph node, call run on that until we get back an end object, and now we've finished. There's a bunch more complexity under the hood of state persistence, which we merged today and will allow you to run graphs distributed over time or compute. But in the end, they're really not that complicated to either understand or use.
Before I go to my next question, I wanted to say I read the overbearing warning at the top of the documentation for the thing that uses the state machines. And I also smiled when I read it because it was really a clever way of saying, be careful, you may not need this. But I think what you're saying is that over time, it's going to be easier for developers to just jump right in and use that approach.
Yeah, I'm more and more compelled that graphs are really useful in this space. And we'll be doing a bunch more work on them. But yeah, I think they're really useful.
Now, when you were talking at so many different times, when you said a phrase, it made me think like, oh, that's a little bit like LiteLLM, or oh, that's a little bit like LangChain, or wow, that seems a little bit like Instructor. So I'm wondering if you could kind of go through the AI LLM landscape and then maybe make some connections between Pydantic AI and then things like LiteLLM or LangChain or other tools of that nature.
So I'm a big fan of Instructor. Jason, who built it, is a friend of mine. I think he's a bright guy and done some interesting things. He's also been enormously valuable to us as a company. He gave a talk at the first AI Engineer titled Pydantic is All You Need, which I think is part of the reason that Pydantic is now so ubiquitous in that space. Without wanting to be rude to people who've built other libraries, I'm not particularly impressed by any of the other agent frameworks or libraries. The engineering quality is generally much lower than you would see if you looked at the leading Python packages outside of the space of AI. And that is, to some extent, not very surprising. The people who have built these things are not generally experienced open source or Python developers. They're AI experts, so we're building the thing they need. And well done, and that's useful of them. And we've obviously been able in places to build on top of what they've done in terms of learning from what they've done. But none of them, I think, have the engineering rigor that we would expect of a library we would maintain or as I say, of a library in the rest of the Python ecosystem. We're not the only people by a long way who've built great Python libraries. But if you go and look at requests or HTTPX or Rich or FastAPI or NumPy or Pandas or a whole host of other well-known Python libraries, go and look through the Python top most downloaded 100 Python packages. And there's amazingly high quality of engineering in most of those libraries. And yet you switch over to LLMs, and maybe this is what happens always when you have a kind of new space where people are innovating quickly, but the engineering quality is just not there. If you go and look at test coverage, if you look at type safety, if you look at even using linting, even testing on all recent Python versions, there's an agent framework, not one of the ones you've named, that was released last year by a relatively well-known person in the ecosystem, and it had something like 25 tests. It didn't have linting, it didn't have type checking, didn't even have proper documentation. These things are built in cases by opportunists, and the quality is not that high. And so what we wanted to go and do was build an agent framework or an LLM library that prioritized good engineering quality and doing things properly over necessarily implementing the latest hype cycle or fad as fast as possible. I say the Django, but the Django or the FastAPI of the LLM space, the kind of dependable workhorse that's going to do things properly, even if we're not jumping on necessarily the next hype cycle immediately.
Okay. I see what you're getting at. And I've actually run the regression test suite for a lot of the top 100 projects that you're talking about. And I've looked at their CI setups. So I know exactly what you're getting at when you talk about the very high engineering standard associated with a lot of projects that are in the Python ecosystem. So just really quickly before we move on to the next topic, you mentioned kind of the hype cycle, and perhaps I'm now using some hype cycle phrases, but can you do things like retrieval augmented generation when you are using Pydantic AI? And maybe could you give us an example of how you do that if it's possible?
Yeah, absolutely. So we allow you to implement tools, of course. I think we have basically the best interface for defining tools. I think that is relatively well demonstrated by how people are now using what we've done and basically duplicating or copying it in places or just relying on Pydantic AI. And the rate of adoption of Pydantic AI in terms of downloads has been astonishing. But within a tool, you can then go and call a database to search for an embedding, for example, perfectly easily. That will work very well, generate the embedding and search for the embedding. We allow most of those things. We allow you to do the more complex things like React, chain of thought. That will all work within Pydantic AI. We have all the primitives for those things. We just think that it's more important to get the typing correct, get the library to be well tested and have good primitives than to necessarily have the example of all of those things.
So I'm going to ask this next question in perhaps a slightly strange way, but suppose I don't use Pydantic AI and I simply go to the documentation for Claude and I see that there is a way for me to write a Python program that can interact with their LLM. What would go wrong for me if I didn't use Pydantic AI?
I've been a little bit rude on this podcast about some of the other agent frameworks, but I think generally the quality of the SDKs from the inference providers is very high. And that's partly because they've been built by companies who specialize in doing that. So Stainless and Speakeasy have done an amazing job of building the SDK. So Anthropic SDK, OpenAI SDK, Grok SDK, Mistral SDK. And so those libraries are good in general. The two big downsides of using them directly. One, you don't have the option to switch out to another model that easily. Two, there's a bunch of stuff that you just have to go and implement yourself. It's a bit like if you were to go and implement HTTP parsing by starting off with a socket connection and saying, I'm going to parse the headers directly. Cool, that's a fun thing to do. It's probably a useful thing to do in learning how HTTP works, but it's not something you want to do if you're trying to build an application. So if you want to do, for example, take a Pydantic model, use a JSON schema to define my tool parameters, then validate the response and make another call to the model if response was invalid, that is something that's a pain to do manually. And you would much rather just go and use Pydantic AI to do it for you, unless you think you are going to the IP of what you're building is in how you implement that, in which case, you're totally within your rights to go and use one of their SDKs or even make HTTP requests directly.
So when I've built Python applications that are interacting with cloud-based LLMs, one of the things I often want to be able to do is save the history of my interaction with the LLM. Like, I want to know exactly what did I send it? What did it come back with? How close was that to what I was really hoping for? And then I want to keep all of that state as my program is running. So I'm wondering if you can talk a little bit about the interplay between logging and LLMs as we transition our conversation to a discussion of Pydantic Logfire.
Yeah, absolutely. I think there's 2 points you're making there. One, we often want to store the messages to reuse them to continue a conversation. We want to, when we make the next request to the LLM, we want to include the message thread such that the LLM effectively has the context. Because obviously, if you just make 2 consecutive requests to, let's say, ChatGPT without including the previous messages, it doesn't have any context on what you just said. So it's almost like start a conversation with someone where all they hear is you saying, that's interesting, why do you think that? And obviously they can't answer because they don't know what it was they said before. There's a slight subtlety there that the new Responses API from OpenAI now allows you to basically store that thread within OpenAI. That has some advantages. It also has disadvantages in terms of model agnosticism, but whatever. So the first thing we do, and one of the other added values of using Pydantic AI, is we record this sequence of messages. They automatically get returned to the LLM if you're within the for loop that I talked about. But you could also record them however you want to record them and then reuse them if you're going to re-enter a conversation from another point in your application. But then the other bit that you're talking about is basically being able to see the messages exchanged with a model for observability reasons. So or evals, to try and work out what the hell my application is doing, what the model is doing, and ultimately go about improving it or identifying if it's behaving badly and, stop that. And so that's an incredibly useful thing to do. It's something that there are emerging open standards on how to do it. OpenTelemetry has a SIG, a special interest group, working on semantic conventions for LLMs. We're part of that. I was on the call yesterday working out how we persist those messages, but Pydantic AI already has OpenTelemetry integration, so you can send the data to any OpenTelemetry compliant platform. Obviously, we think Logfire is best, but we think that engineers are bright enough to realize that lock-in is not a good thing and to avoid it. And so we're not trying to make you use our thing through lock-in. We're trying to make you use our thing through it being so good that you want to.
So you mentioned a moment ago OpenTelemetry, and as we start talking about Logfire, the system you mentioned a moment ago, I'm wondering if you could say briefly, what is the OpenTelemetry standard, and why do logging systems like your system decide to adhere to that standard?
Yes, so OpenTelemetry is a standard for communicating observability data, logs, traces, and metrics. And then it is also a bunch of SDKs for every popular language that allow you to generate that data and send it to an OpenTelemetry backend. We are doing something slightly differently. We have Logfire, which is our SDK for Logfire, which basically is an opinionated wrapper around OpenTelemetry. So it makes it more Pythonic, easier to go and effectively generate those logs or traces or metrics and send them off to an OpenTelemetry backend. And obviously, Logfire defaults to sending it to ours, but you can send it to anyone you like. But yeah, OpenTelemetry is an evolving standard. Started off, the first inklings of it were some projects in around 2016, but it's really reached fruition in the last 2 or 3 years. One of the interesting questions is why would the likes of Datadog, the big incumbents, allow OpenTelemetry to happen and indeed go and contribute to it? And although it's not particularly clear, my assumption is that the very biggest organizations, Apple and the US government, for example, said, if we're going to use your thing, we have to be able to use an open standard. Because if we're going to integrate this SDK all over our applications, we need to be able to go and switch out where that data goes, because otherwise we're just too strongly tied into your solution. So that's my guess about why it's come about. Fundamentally, it's not perfect, like all of these open standards that are designed by committee, but I think all things considered, it's pretty powerful. So it can send data over either JSON or protobuf to HTTP or gRPC backends. And it's a pretty good description of what you might want to do in observability. And so on top of the fundamental protocol, they have these semantic conventions. So basically the names of fields for things like the SQL query or HTTP headers or LLM interactions. And so that's what we're talking about here.
So if listeners are interested, we have a Software Engineering Radio episode that is specifically about OpenTelemetry, and we have a number of episodes that are about logging and things of that nature, and I'll link to those in the show notes. What I wanted to do now was to read a quotation to you that directly comes from the Logfire documentation. So it says, automatically instruments your code for minimal manual effort. Can you briefly say, what does it mean to instrument my code, and how does that help me as a programmer?
Yeah, so there are 2 parts to that. One is that there are existing OpenTelemetry integrations and some that we have built ourselves that mean we can go and hook into many popular libraries you're going to go and use and automatically effectively get data out of them. So whether it be a web server like FastAPI or Django or Flask, whether it be a database connector like SQL Alchemy or AsyncPG, PsychoPG, Redis, etc., you can go and instrument them, HTTPX requests, etc. You can go and instrument them, and automatically whenever you receive an HTTP request or make a database request or make an outgoing HTTP request, you will get the information about that, how long it took, why it went wrong, if it went wrong, details like the status code, the request method, the path, the SQL query, whatever it might be, you automatically get that. And so what we generally see is with roughly 5 lines of code, 5 to 10 lines of code, you get 80% of the value of instrumenting your application. And you can also integrate Logfire into standard library logging. So if you have logs in your application code or even in third-party libraries, they can come into Logfire as well. And so without polluting your code base with lots of Logfire calls, you get 80% of the value with those 5 to 10 lines of code. And the same applies to OpenAI SDK or to Pydantic AI or to the new Agents SDK from OpenAI. So but then the other bit of auto-instrumentation is a very clever thing that Alex built in our team, where basically at import time of a module, we edit the AST to insert traces into function calls that take more than a certain period of time. So we basically get something more like profiling within your application as it runs, which is an amazing piece of work from Alex. Very useful, but generally not required in most applications, but super useful. If you're what's slow in this module, you can go and say auto-instrument, say I only want to instrument function calls that are longer than 10 milliseconds, and it'll go and do that for you.
So that's really interesting. And I didn't know that's how it works. But basically what you're saying is at runtime, for code that is somehow slow or likely to be slow, you instrument the code in the AST level, and then it will do all of the logging for me. And I didn't have to put the instrumentation into the framework that might be the slow part of my application. Did I say that the right way?
Roughly, yes. Yes.
Okay, so that's really cool because you're actually changing the abstract syntax tree of the program at the point when I load the code at runtime?
Yeah, exactly. That's the sort of thing that we are able to do because we have our own SDK, where if you're using standard OpenTelemetry, not only do you have these like 50 to 100 lines of boilerplate to set up OpenTelemetry, but you don't get things like that. We also have this like neat interface for doing logging and tracing. So logfire.info, logfire.span, where you can send through keyword arguments. They will become attributes. We'll show them nicely in the Logfire UI. Alex has a neat bit of code where we will go and if you use an F string instead of having effectively a normal string template and then variables as you would with logging, we will go and extract the values from inside an F string and show them as well.
Wow, that's cool. I would find that helpful. So if I'm writing something that uses FastAPI or HTTPX, what I'm understanding is that you basically already have an integration for FastAPI, which makes it then really easy for me to use Logfire as my logging system.
It's tracing technically, but yes, most people think of it as logging. But you'll do import logfire, logfire.configure, then you do logfire instrument FastAPI, logfire instrument HTTPX, logfire instrument whatever the package might be. We have 10 or 20 different packages available automatically there. And that's all you need to do to then start getting, in the case of FastAPI, like I say, the HTTP request information. In the case of a database connector, the SQL queries and how long they're taking.
So I don't want my question to sound silly, but many of us are used to writing to like a rotating log or like there's some socket that we're listening on in order to capture the logging information. My question is, where does all the logging information go when you're using Logfire?
So when you're using Logfire by default, running Logfire, and this is actually we're just using the standard OpenTelemetry SDK for this in the background. So it's like very battle tested, very low overhead. We're running a separate thread where we're sending data about each individual log statement. So that might be as simple as the message, but also things like timing on a request. But also you could log something like a Pydantic model or a data class or a date time or even a data frame. And we'll send enough information about that to go and recreate the repro view of that in Logfire. That gets sent to the separate thread. From there, it is sent over HTTP to whatever OpenTelemetry backend you're using, Logfire being the easiest one and the best one. And then in Logfire's live view, you can then see that log line come in. You can see all the data about it. You can see how long a function took to call or whatever it might be. And you see that in a trace, which is basically a nested log of everything that happened within, say, a function call or a HTTP endpoint.
So many Python programmers are probably most familiar with the built-in logging package. Can you say one or two things about how Logfire is different than that built-in package?
Yes, so as I said, we have a few neat things like we're using F-string style strings, and we'll even interpret the values from inside F-strings. But the real power comes from logfire.span or the decorator logfire.instrument, which is the same thing, which allows us not only to have this like linear list of events that happened, but we have this tree structure of logs and where within what other log, let's call it, it's technically a span or a trace, where things happened. And so instead of having this linear list of events and it not being trivial to work out what happened where, we get this like tree view of everything that happened within your application that both matches your mental idea of how your application runs, but also just gives you far higher fidelity on what's going on.
Yeah, I see what you're saying, because essentially when I'm using the logging package built into Python, I essentially have to put all of the logging statements in the right spot myself in order to build up that understanding, whereas Logfire is doing a lot of that automatically for me through the automated instrumentation.
Yeah, exactly. But both through the automated instrumentation and through the system of spans and traces. So if I do with logfire.span, start my function, and then inside that I do another logfire.info or another logfire.span, that all comes through as a nested structure that I can see in Logfire's live view, and I can understand what my application is doing. That use of tracing, it feels like logs, but that use of tracing is the thing that like fundamentally is the game changer.
So this has been both a fascinating and fun conversation, and I know we could have talked quite a bit more about any one of the three frameworks that we've discussed. But as we draw our conversation to a conclusion, I guess I have two main questions for you. Number one, as you've been building all of the tools, Pydantic and Pydantic AI, and then also the Logfire system, is there some lesson that you have learned about building and maintaining top quality frameworks?
Yeah, I think there is enormous value in following open standards. So, for example, following OpenTelemetry, sure, it has some limitations, but it's enormous amount easier for us developing because we just know what standard we're going against. We don't have to go and build that. But also, it's incredibly valuable for users who know that they're not going to be locked into Logfire, so they can use us with confidence. Same, we haven't talked about our database in Logfire, which is incredibly powerful. It allows you to write raw SQL to go and query your data. But we haven't gone and built a database from scratch. We've gone and collaborated with Data Fusion, which is an Apache project. We talk to the maintainers once a month, where we have given them shares in the company, bluntly, as in we've gone and allowed them to share in our success. And we find that to be a much better way of building than to go and build things ourselves. So whether it be open standards or existing projects, same as Pydantic using type annotations as the definition of the schema, sure, it has some limitations. Python's type system isn't perfect, but it is way more powerful for users and way easier for us that we know what the source of truth is in terms of the standard.
Yeah, that makes sense. And instead of going out and building your own bespoke type system, you're leveraging what exists in Python, which means you're going to get way greater adoption than you would otherwise.
Yeah.
So the last question essentially has two parts. And the first part is do you have a call to action for our listeners of Software Engineering Radio? And then finally, is there anything that we've overlooked that you wanted to briefly highlight?
In terms of what we've overlooked, we have some really exciting announcements coming up over the next couple of weeks, which I presume will be out by the time this podcast is released. So I would have a look at we'll have a blog post up summarizing. I think we're calling it Rolling Thunder. We have 8 big announcements coming up over the next 8 business days. So I would really encourage you to go and have a look at them on either on Twitter or on our LinkedIn or on our website. And those will be really exciting. Obviously, the main call to action is I'd love people to go and try Logfire, give us feedback. Same with Pydantic AI. You can join our Slack. You can ask questions. It will be me or the others maintaining the project who will answer. And I'd love to hear people's feedback, good, bad, or indifferent. We're always interested in how people are using these things. And then the final point, I can give a sneak peek. The first of those announcements is that we're hiring a bunch more roles next week. So if you're interested in working with us, hopefully not all those roles are filled by the time this podcast goes out. And yeah, go and have a look and see if any of them interest you.
Thanks for all those details. This has really been a fun conversation where we've done a deep dive into 3 frameworks. If listeners are interested, there's a whole bunch of other shows that we have published on Software Engineering Radio. They're connected to the topics for today, and I'll make sure to link to those in the show notes. Thank you so much for being here on Software Engineering Radio today. It was a lot of fun to chat with you.
Really enjoyed it. Thank you so much.
Thank you, Samuel. Bye now.
Bye-bye.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.